Good morning. Sorry, I was a little late. Computer was having some trouble signing into Zoom earlier. Luckily, I am here. All right, so let's continue to have our discussion about universal gravity. And if you still remember the formula to describe the gravitational attraction between any two objects with mass is the gravitational constant, capital G, times the multiplication of the two masses divided by the distance squared. Okay, so that is a formula we've talked about. All right, let's check our understanding really quickly with this question. It should be really quick. If the distance to the moon between the Earth were doubled, what do you think will happen to the force? Okay. All right, so 10 more seconds. All right, so any last minute? All right, I'm gonna go ahead and end this. Okay, it looks like we are in agreement about the force. Again, this is what we call a inverse square law, right? So if the distance doubled, the distance became 2D. So you can see the force would be 1/4 what you had before, right? Because this is 1 over distance squared. So if distance doubled, the force will be 1/4 of what you had before. Very good, A is correct. Let's take a look at another question. This is very similar to before, but we now have to look at the gravitational attraction from two different sources. So here we are looking at the forces on Earth. Let's say you have one object over here with a mass m, another object here with 2m, and the distance are, one of them is a d, one of them is 2d respectively. Okay, so when you have two forces together, the overall total force acting on the Earth could be best represented by which of these vectors, okay? So there are 5 different options. So it doesn't have to be exact, but we're just trying to figure out relatively where would the force be pointing at, right? So for example, A would claim that the force is purely vertically down and E is purely horizontal, and C is right in the middle, like a 45 degrees, and D and B means a little bit tilted up or down. So which one do you think is correct? So this one we'll have a discussion in our breakout rooms for a minute or two. Before you head out to your breakout rooms, please make sure you take a screenshot of this question, okay? I believe I will be joining room group 7 today. Okay, hello, Michael and Spencer.
Hi.
What do you think about this question? Like, how do we get started?
We could plug it into the formula for the force.
Okay, all right, so let's do that, Michael. Let's say the force, so there's a force in this vertical direction here. I'm gonna call it the force in the y direction. There's a force in the x direction as well. The force in the y is g mass of the earth, mass of the other object divided by d squared, right? And the force in the x direction would be g mass of the earth and mass of the other object divided by 2d squared. So now we plugged it into the formula. From there, what can we tell?
That the force, I think, to y is stronger than it is to x.
Oh, okay. So this is stronger than this. And how much stronger can we tell?
That'd be, yeah, like, I think, yeah, 1/2.
Okay, yes. So yes, so if this is stronger than this, let me modify my picture a little bit. If I draw it to scale, I would say, okay, the vertical force is this much, the horizontal force is this much, right? So only half of the vertical force, okay? All right, so based on these drawings, which one of these is correct?
It would be B.
Yes, very good. It should tilt a little bit more downward because the vertical component is stronger. Excellent. I will see you shortly in the main session. All right, so if you haven't voted already, we will go for 10 more seconds. Okay, any more votes, Thomas? Okay, all right, I'm gonna go ahead and close our poll. We'll take a look. All right, looks like we do have a majority agreement on one of the choices. So would anybody be willing to share their thoughts? How do we figure out what the direction of the total force is?
So what I did is that, so given the formula that it's G, M1, M2, all divided over r squared.
Okay.
Basically just did both cases. So from planet, let's just call it M.
Okay.
It's G, just one total mass over 1D.
Okay.
And then the 2M planet, it's G 2M. Well, yeah, two total masses divided by 2D squared. So that would be 2 over 4, which is 1/2.
Okay.
So the A planet, yeah, the M planet is two times larger in terms of force.
Okay.
So that means the vector has to point more towards it. And like C looked like a 45-degree angle to me.
Okay.
So that'd be if they were balanced, and they're not. So it's not completely vertical because 2D, the 2M planet exists. So the one that was kind of in between A and C was B.
Yes, excellent. Thank you so much. We plug into the equations, we realize the vertical component is bigger than the horizontal component, right? So when you add up two forces, that's like this, is going to be sort of more diagonally downward toward, more close to the vertical direction, but not 100% vertical. Thank you so much, Juan. That was excellent. Okay, so B is the correct answer. Again, you can see here, we would just apply the universal gravitation equation. Now let's continue. We were talking about how we could calculate the little g from the big G, right? And we know that the attraction is mutual. We, as Earth are pulling on us, we're also pulling on the Earth. So let's say you're standing on the surface of the Earth. What is the acceleration that the Earth experienced due to your gravitational pull on the Earth? Okay. Now, you probably already imagine this will be very small acceleration for the Earth, because the Earth will be so massive, and that little bit force, even though it caused a 9.8 meters per second square gravitational acceleration for each one of us, but it might cause a very little acceleration on the Earth. Okay, so will we be able to calculate this using the formula? And again, the force between you and Earth is G mass of you times the mass of the Earth, right? Divided by the distance between you and Earth. Now, we always, when we look at two objects, we're counting the distance from the center of the mass of these objects. So if you're counting the center of mass of the Earth to be the center, then from the Earth to you are so tiny compared with Earth. So we don't even ignore your height to think of you as a point. So the distance from you to the Earth center is basically the radius of the Earth, right? So it's a radius. Now here, we can use D to represent it, is the distance between you and Earth. Okay? So from that, we'll be able to find out the acceleration Earth feels. So I'm gonna go ahead and let you vote on this. Okay, so I just wanted to clarify, when we do the calculation normally, when we try to find out the acceleration, we simply just treat D is equal to radius. But when you are given more accurate options, then you probably wanted to use that. Now, for example, if you do know the distance between your center of the mass and the center of mass of the Earth, then we do want to use that option just because it is a little more accurate. But in our calculation, we usually don't do that. We simply just use the capital R to represent the distance. All right, so we're gonna use this more accurate definition. So if you wanted to choose between these different answers, it looks like it's more of a difference between C and D. Okay, sorry, I was not looking at C and D earlier. So we do have more accurate choices here. Okay, let's go for 10 more seconds if you haven't voted already. All right, any last minute vote before I close? All right, let's take a look. The only difference between these answers is really, should we use the mass of the Earth or mass of your mass? Now, knowing that we are expecting a small number, right? We said the acceleration on the Earth would be small. So you probably know that you should use your mass, because if you use Earth's mass, you're not going to get something so tiny because Earth's mass is so big. So how do we get this acceleration exactly? We know that the force acting on an object is equal to mass times acceleration. F equals ma. That still works. That's still Newton's second law, right? And in this case, we're looking at Earth's acceleration. So you should use mass of the Earth times Earth's acceleration. So it's going to equal to mass of the Earth times the Earth acceleration. So m of the Earth cancels. You can see the acceleration of the Earth is equal to g times mass of u divided by d squared. So D is correct. Very good. Very good. Okay, so now let's go back to figure out what is our acceleration. What's your acceleration? Okay, so if we do that, we say, okay, the force on you is equal to g mass of u times the mass of the Earth divided by, here with the estimate, we're just going to use the radius of the Earth squared, okay? That's the distance between you and the Earth. That's equal to F equals ma. This is mass of u and acceleration of u. Cancel your mass. Now you see that the acceleration that each of us feel, each of every object on Earth feel is regardless, does not depend on your mass, because you can see it get canceled from both sides, which makes sense because the little g is the same for everyone, right? Not everyone get a different acceleration. We all get the same acceleration. And that acceleration is g times the mass of the Earth divided by the radius of the Earth squared. That is the acceleration of u. Now we can do this really quickly to see, is this really going to be 9.8 meters per second square? You can plug in g and the mass of the Earth. All of these is already in SI units, so I know my results will be in meters per second square. Okay, divided by radius squared. And this will indeed give you 9.8 meters per second squared. So it's going to be a little bit different at different places on Earth, because you know that the sum of the mass of the Earth is not purely homogeneous, right? And as you move at different locations, that sum of mass will change a little bit. So it's not going to be exactly the same, but it's very close. Okay, so here I got 9.86 meters per second squared. This is just a rough estimate, right? Because you can see that we simply just use the radius of the Earth to calculate. Okay, this is very close to the little g that we normally use for our acceleration on Earth. Okay, so now we'll move on to talk about gravitational potential energy. So we say that, okay, well, we have mgh as our gravitational potential energy. But now, since we have a more accurate definition for this force, you can see that this force is not a constant, right? Approximately when you're close to the Earth's surface, this force is always mg. But to be more exact, you can see this force is depend on the distance. So the force changes as you move further away from Earth. Then the force becomes smaller and smaller. Okay, so it becomes less trivial and more important to treat the force as a variable, especially when you're talking about having a distance change relative to Earth, right? So when we're talking about launching satellite, we're talking about astronomical objects, the R is not constant, and the force is definitely not a constant. So we cannot treat the force as a constant and say gravitational energy is always mgh. That would not be okay. So this is only when you're looking at the surface of the Earth, you're not going anywhere, right? Because when you're going, if you're leaving the Earth, you're moving any significant amount of distance away, the force is no longer a constant. So we can get this formula by looking at the work done, because we know that the change of gravitational potential energy is equal to the work done by the force. Remember? Because that is sort of just a different point of view of what is your system. Earlier we said, okay, the work done by Earth, gravity is mgh. If you exclude Earth from your system, but you can shift a different point of view, saying if you include Earth in your system, then the change of potential energy is mgh, okay? So we can get a formula for potential energy by looking at the work done. The work done is F times dl, remember? The integral of force over displacement. So if we simply treat dl, the length to be the same as the radial component pointing toward the center of the Earth, dr, then you can calculate the work done, and you'll get one of R dependence for your work, right? So this is 1 over R squared. When you integrate, you get 1 over R. So gravitational potential energy is defined between any two massive objects here. Any massive objects is defined to be negative gm1 m2 over distance r, and is a function with respect to the distance. Now you might wonder, okay, why negative? That's because where is your reference point? As you can see that we said reference point is totally up to you. It is arbitrary. You can put your reference anywhere. It's all relative, right? If I put it at my table, then here you have mgh being maybe 20 centimeters. This is how far it is away from my table. So as a convention, people pick the zero gravitational potential energy point to be at infinity. This is not the only way, but this is the way that people commonly choose to do. With that convention, if your infinity is far away, then when you're not at infinity here, you have a negative number, okay? So this is, I know this is different from how we normally do with our daily life calculation. We often treat the sea level as 0. So everything compared to the sea level, you're on top of it, right? So you have positive potential energy. Here we're treating infinity is 0. So we're not at infinity. All our gravitational potential energy is negative when you are not 100% away from the Earth gravitational pull. So when it's negative, it's simply saying you're still under the influence of the Earth's gravitational attraction. When you're going infinite far away, when R approaching infinity, then you can see this U potential energy approaching 0. Okay, now with that definition, we're able to answer a few more interesting questions. The first question, let's look at it together, is about orbiting around the Earth So what is the speed required for an object to go around the Earth? And let's say it's at a distance r away from the center of the Earth. So if this is the Earth, and this object is at radius r away and is orbiting around circular motion. So think of this as a satellite. Okay, so this will affect our calculation. Okay, what is the speed required for the satellite to go around the Earth at a particular trajectory and it's at radius r away? You know that if the speed is not fast enough, it will fall back into Earth gravitational pull, right? Okay, so let's take a look at this question. And I will give you a hint that if this is a circular motion, we know that F is equal to ma, and acceleration for uniform circular motion is v squared over r. Okay, so maybe that will be helpful in answering this question. Okay, so this one, let's go to our breakout room for a discussion, and when we come back, we can vote, right? So take a screenshot before you leave, and I will see you when you come back. So I will go back and go around back to group 1 for this question.
Hey, Professor.
Hi, Juan, Carlos, Joshua, and Julian. Okay, so what do you think about the velocity required? What is the speed required?
Professor, are you? Oh, hey.
Were you muted? I think you were temporarily muted earlier.
No, I was trying to tell you that I couldn't. I saw you come in, but I couldn't like hear you. So I was asking you if you were muted, but then I saw you put up the screen.
Oh, yeah. Maybe as I was talking, I was clicking the unmute button, and then yeah, it got cut off. Yeah.
Oh,
So, okay. What do you think about this, everyone? So we have this
The question
equation.
first.
What is the next step?
With the next step, we could since it's v squared over r, and we could probably just try to right now isolate for v.
Okay. Okay, so this force between the satellite and Earth is mv squared over r, and this is, do we know the force? This is gravitational attraction between the Earth and the satellite, right?
Mm-hmm.
Okay, so we can make this equal to what?
F times r divided by m1 square root all over that.
Okay, all right, and again, we still don't know the F, right?
Mm-hmm. And that would be m Earth times m1 over r squared, and then the coefficient of g.
Okay, so gm1 m Earth over r squared.
Yeah.
All right, so from here we can calculate our velocity, right?
So then m1 cancels, one of the r cancels, and then so then we just have square root of well, V equals square root of G ME over R.
Yes,
So I think it's A.
yes, that's it. Very good. Excellent. Okay. All right. So I will see you in the main session then. Good job. All right, so let's wrap up our vote. 10 more seconds. All right, any last minute vote? I'm gonna go ahead and end the poll. Let's take a look. All right, realize that we had talked about how the acceleration for each of us does not depend on our individual mass, because the m of our mass will be canceled out from the two sides of the equation. So here is the velocity. It's probably the same way, right? The velocity should also not depend on the individual mass of the object, because when we set up the equation of F equals ma to the gravitational attraction between these two objects, the mass of the satellite appear on both sides. Okay, so this force is Gm1, mass of the satellite, and mass of the Earth divided by the distance between them squared. So you can see that we can solve for velocity required, right? Velocity required to be square root of Gm of the Earth divided by the distance between them. So yes, A is the correct answer. So it's A. Right, so that is the velocity required. Anything less than that, it would not be able to keep in the orbit. It's going to fall. All right, so now let's take a look at another question. So even though the satellite is orbiting around the Earth, it is still under the gravitational attraction pull of the Earth. So it has not escaped Earth yet, right? Earth is still keeping it in its orbit. If we wanted to be able to escape Earth just completely free of Earth's gravitational pull, then what is the minimum speed required for an object? Imagine that probably going to be much bigger than we had before, right? Because if we wanted to completely be free, we need even higher velocity, more energy. Okay, so this one we'll do it together. There's a hint. What do we mean by escape? Simply that you're free of Earth's gravitational field. Now, if you're free, means that you are not under the influence when your potential energy will be zero. You're basically at too far away, infinitely far away, and U is zero. Okay, so we wanted to try the minimum speed required for you to be able to be free. So this is the speed on at Earth's surface. So imagine to be free, you would be launched at a very high speed, and eventually, a very far distance away, you are free. So this is, you probably see the physics approach for this is going to be energy conservation. So we're going to use a conservation of energy approach to look at this question. So we're looking at the initial state when you're still at the Earth's surface. So your initial energy, well, would be kinetic energy, right? So you have a very, very high speed, mass of U, a very, very high speed. Okay. And while you're at Earth's surface, you still are under the influence of Earth's gravitational field. So you have potential energy. So we tend to use U for potential energy when we're talking about universal gravitation. We're not just talking about being on Earth. Everybody's on Earth, we do PE, right? Potential energy. So when we're talking about universal gravitation, especially involving astronomical objects, we use U to represent it. But you know, it's just potential energy. And if you did use PE, it's not going to consider it wrong. Excuse me. Okay, so you have these two parts of energy when you are at Earth's surface. And eventually when you're free, we know that you will have zero potential energy. And do you have any kinetic energy? Well, that depends on what the question is asking. The question is asking minimum. So what does the minimum mean? Means that you're launched with the speed just barely get you to be free of Earth's gravitational field. When it's just barely to be free, that gives us a critical condition of your kinetic energy at far away is when you're just about free, you're also at a zero kinetic energy. So you just got free and then you also stopped. That's the bare minimum. If you launch with speed more than this, then when you're free, you're still going, you continue to go. But the minimum required is when you're just free, you just stopped. That's the minimum you need, right? Okay, so now we have all our energies and there's no inputs and outputs, obviously. Here we're treating Earth and the object to be the system. The force between them is internal force, there's no external force. So we have no energy inputs or outputs. So EF minus EI is equal to energy transfer is zero. So we just make these two energy to be equal. E final is zero energy. And what is your initial? Initial is your kinetic energy plus your gravitational potential energy. And we talked about that is negative over R. Okay. All right, so combined, these two combined will be able to help you solve for V velocity minimum, and V is going to be, again, M1 cancels. 2G M Earth over R and square root of that. Right? So it's going to be this choice. and it is bigger than the orbiting space, orbiting velocity, apparently that much bigger because you need more energy to be completely free of Earth's gravitational.
Professor.
Yeah.
So I have a question about like the concept of that. So doesn't technically the gravitational field pretty much expand to anywhere in the universe? So it's like anywhere, like let's say I'm here,
Mhm.
I don't know, probably gonna butcher the pronunciation, but I'm also getting affected by the gravity of Alpha Centauri, but like I'm super far, so it really doesn't do much. But it's like the field still technically affects you.
Of course, but
So it doesn't.
like you said, it's affects you, but it's so far away. You can consider your potential energy due to the moon's gravitational to be zero. So in this case, because you're far away, we consider that you are now no longer under the moon's or the sun's or Jupiter's gravitational field.
So basically, when we're saying that escape means the object is free of Earth's gravitational field, that just means that it could never keep you stationary or pull you back in.
Right. You are now free
Okay.
to go elsewhere.
Okay, cool. Thank you.
Okay. Very good. So that is and this equation is universal. So you can switch this mass of the Earth to be anything, like say any planet. What is the escape velocity required for Mars? Then you will do square root of 2g mass of the Mars divided by the radius of Mars. That is the escape velocity for that particular planet. And that is a universal equation that you can use for any planet. Okay, so the minimum velocity required to escape from any planet is a square root of 2 times g times the mass of that planet divided by the radius of that planet as a rough estimate. All right, so we have a few more questions here. Let's take a look at them together. So let's look at this one. There's an explorer, and where would the weight of that person be greater? We had talked about, you know, at different places on Earth, you're gonna weigh, if you weigh yourself, you're gonna see different numbers because the little g is different. And that is really just because this equation will tell us that this force is a little bit different at different locations, right? So this gets to more of a fundamental level of how come that your little g or your weight is different at different locations. So they give a few different choices. For example, we are at this summit of this place, which is a distance of 6,384 kilometers from the Earth center. Or if you're at a different place that is much lower or on the surface of the Earth's equator line, that I need to give you the numbers. All right, I have a question. All right, so I got a request to go back one more slide. I will do that.
Thank you, Professor.
Okay, good. All right, so let's take a look at this. Okay, so you have to look up, okay, what is the distance from the Earth center at the equator line, and we will get that number. So where would the weight be greater? You can see, okay, what is our weight? What is that we're measuring? What we're really measuring is the attraction between the person and the Earth. That is the force. And that is a force we measure on the scale, right? So we can see that, okay, what has changed? By going to different, this is really just your weight. By going to different places, your mass remain unchanged. It's still the same person. The mass of the Earth overall doesn't change. It's still the same Earth. The only thing that's changed is your distance between you and the center of the Earth. That has changed. So if you want the greater weight, we just need to look at where you are closer to the center of the Earth. That gives you a bigger force, because when R is smaller, then the force is bigger. So we compare these different numbers, we realize it turned out that the second location is the smallest distance because we can look up the location for the equator line is also still going to be a little bigger than the second location. So whichever has a smaller distance, you have a larger force of gravity. Okay, so that explains why you weigh yourself here, or go to the North Pole, or go to the equator, you're going to get slightly different numbers. You're using the same scale and assuming everything else stayed the same. All right, that's one question. All right, let's look at one more question, and then the rest of that would be Kepler's laws, and we will talk about that on Friday. So the second part of this question is, okay, we're still looking at different places on Earth, but now we're trying to compare something different. The explorer visited 3 different places and she raised her hand. There is a change in potential energy, right? So where would that change in potential energy be greater at different locations? Again, the locations are the same. We're simply just going to look at the change in potential energy. So this one, we do need to draw a diagram to look at it more closely. So what really is changing, you see that, okay, this is the center of the Earth, and this is location 1, this is location 2, right? And I'm going to call this is distance R1 and this is distance R2. And by going from 1 to 2, you can see, well, I have raised my hand by a distance of h, for example. So now I want to see the change in potential energy from 1 to 2, which one is greater? This is what the question is asking. And we are given the result formula for potential energy. As we said, to be more accurate, the potential energy now is a function with respect to your distance r. It is one of our dependents. There's a negative sign. So we're going to use this more accurate definition. So the change in potential energy between 1 and 2 is your potential energy 2 minus potential energy 1. Okay, there's always the later point minus the earlier point that describes the change. Right? So that is negative m1 m2 over r2 minus negative m1 m2 over r1. Okay. So that becomes gm1 m2 1 over r1 minus 1 over r2. This becomes a positive sign, and r2 has a negative sign. So I factor out gm1 m2, and what's in the parentheses is 1 over r1 minus 1 over r2. Okay. All right, so let's further to factor out the variables that that does matter. So R1 is the one that's different. So here you always raise your hand by the same height. So that H doesn't change. So what is different is R1. If you are, say, at the Earth's equator, the R1 we said is 6,378 kilometers. If you move to a different distance, the R1 is different. So that is what's different between these different quantities. So we know that R1 is different. R2 is simply R1 plus the extra height by raising your hand. So we can make this into a purely a function with respect to R1 only. So this becomes R1 plus H, H over that. Okay, so this is only a function of R1 because everything else is the same explorer, the same Earth. You raise your hand by the same amount. So if R1 is smaller, then overall this is bigger. Okay, so again, if we're looking at the smallest R1, you're going to have a biggest change in your potential energy. So the answer is B. Okay. Again, you can see this is really a practice on using this formula. This is a question of that help us understand and use this particular formula. All right, so that's all for today. On Friday, we will do the rest of the universal gravitation, which included Kepler's laws. We'll talk about that. And we have extra time. We will move on to talk about simple harmonic motion. That's our second to last topic. All right, bye everyone. I hope you have a good rest of your week and see you on Friday.
Professor, when we're doing the integration, you know how you got G M1 M2 over R,
Yes,
but you still kept it negative?
yes.
When you like for that particular integral, the sign would change. So if we started with a negative, shouldn't the sign become positive? Or for the purposes of our calculations, do we just ignore that because it makes life easier?
Well, okay, let me go to that page here.
Okay. Yeah.
There is actually a negative sign coming out of this because you can see 1 over R squared dr is negative
Mhm.
1 over R.
Yeah.
So when you say there was a negative and there wasn't a negative, there wasn't a negative before, right? This is positive, and then you get a negative coming out of it.
So then, because it says on the left side of the screen, it says U grab equals negative. Oh, I see what you did. Sorry, okay, I see. I'm sorry, I got confused with how you did it. I misread one of the graphs, like one of what U grab was initially. So I thought you did it. You made the the F part G equals M1 M2 over R squared negative F first. Okay, that makes sense. Thank you.
Right, but I do want to let you know I hand waved it. The details is more complicated, but I don't want to go there because, okay, this integral, whether it's positive or negative, depend on a few different things. First of all, which direction is your force and
Yeah.
which direction is your displacement. So if we're talking at, okay, Earth and an object, then the force is this way. And is your displacement also that way? Is your dr also pointing in? Now, which means that you're going from infinity to Earth. Okay, that dot product will be positive. But if you're going from Earth to infinity, then your dr is this way, and that dot product will be negative. So that's one of the nuances that could affect the sign. Also, you can see the integration limit could affect the sign. Are you integrating from infinity to R or R to infinity?
Yeah.
And that's just the work done. You still have to translate the amount of work done to the gravitational potential energy, right? So if I'm going from here to here, the work done by Earth is negative. You can see I'm going up, it's negative.
Yeah.
The change in gravitational potential energy is positive. I'm going from smaller to a bigger number. So that introduces another negative sign. That's why you got to be very careful. We could eventually arrive at this result, but I don't want to go that way. I think what we should do is, okay, we will just use the work done to give us a absolute value of the magnitude of the potential energy. And then we think about, okay, do we want it to be positive or negative by thinking about where is our reference point? Now, reference point at infinity, then we should use a negative sign.
Okay, so then
That's
that's okay.
This
So it's
is
pretty
really
much
very hand-waving way of doing things.
okay. So it's pretty much it. The sign can depend on it'll depend on the situation, just like usual.
Yes.
Okay, cool. Thank you. Sorry, I just wasn't sure why I was like, I thought it was always going to be negative. That's what confused me.
Yes.
Okay, thank you.
Very
Have
good.
a good day.
Thank you. Bye.
Bye.
Thank you. Bye, everyone.